and welcome back to our video series on analysis of variance. So far, we've covered completely randomized designs, we've covered multiple comparison tests, and we've covered linear contrast. Now, we've also assumed homogeneous conditions. We assumed the treatments were applied in the same field in our crop data. But suppose we have the following situations. Our field has different elevations, or perhaps our fields are in different areas. Now, in either of these cases, we have no control over the environment. If we have different elevations, the average for our fertilizer brands are also averages for the elevations. Different soil solubility is available in different elevations. So imagine a field that has three levels, perhaps a flat top level, a sloped middle level, and a flat bottom level, such as this. Well, when it rains, our top level has nice solubility, as opposed to our middle level, where our rainwater is running downhill. And then at our bottom level, we still get the rain from above. However, we also get runoff from our middle level. So in our top level, our water is slowly absorbed by the soil. Our middle level, water runs downhill, so soil solubility can be diminished. In our bottom level, water from level 2 is also added to the water from level 3. This possibly causes too much water and subsequent flooding through supersaturation. Or perhaps we have fields in different areas, and our soil content may not be the same. So now the averages for our fertilizer brands are averages for our areas as well. In either of these cases, there are variants which we have not accounted for. In our sloped field, there's variation in our soil saturation levels, so variation in brand A may be due to different saturation levels, and not necessarily in our treatment. In our different areas, the variability in our soil types could mean that the variability in brand A is due to the different soil types and not the treatment. When this happens, it's appropriate to run what's called a randomized complete block design. Now, a randomized complete block design takes these differences into account, and it provides some local control over the environment. We reduce our experimental error by grouping our experimental units. This provides less variability. This is because we're providing less variability within group units than all unit variability prior to grouping. So in our randomized complete block design, these groups, these blocks, are going to stratify our experimental units such that our blocks are now homogeneous units. In other words, we could look at, for our different field levels, our top level is one block, our slope level is one block, and then our bottom level is one block. If we're talking about our areas, well, different areas would be different blocks. This homogeneity of units provides increased precision and increased homogeneous effects for our response variable. In other words, we have more uniform environment, and this allows us to identify differences in treatments by removing the confounding effect of large differences within our experimental units. So blocking provides the experimenter the ability to distinguish between variability due to group differences and the variability in experimental error. So our experimental units are blocked into groups because we know there is a difference. What type of criterion would cause us to want to block? Well, proximity. Neighboring field plots should have similar characteristics as opposed to those that are separated by greater difference. Physical characteristics such as age or weight. Time characteristics such as hours, days, weeks, months, or years. Experimental task management such as differing laboratory technicians. Other blocking examples can include animal litters or homogeneous batches of raw materials. So perhaps you have an experiment requiring iron material, but you need more than what you can obtain in a single batch. Well, each batch may have a different iron percentage, and so these differences yield variations from batch to batch, thereby increasing experimental error. So we would block by batch. Now, if our response variable is affected by factors, and these factors vary among experimental units, our experimental error increases, and this causes decreased precision of experimental results. So, what does this mean? This means blocking reduces and controls experimental error and increases precision. Now, the simplest randomized complete block design uses one blocking criteria. We can use it to control and reduce experimental error. Our experimental units are split into blocks of homogeneous units, and each treatment is randomly assigned to an equal number of experimental units in each block. Now, as an example, suppose we have 5 different nitrogen fertilizer levels and a control of no fertilizer. Our experimental design is going to be on a large scale, and so we need a large amount of land. However, we're unable to utilize a single plot of land. So instead, we need to use 4 plots of land, and each plot is in a different area. Now, each plot has different soil nutrient levels, and so we'll use these 4 plots of land as blocks. Therefore, any differences in perhaps corn yield caused by nutrient levels can be associated with the blocks. So what we've created is a randomized complete block design with 4 blocks, our plots of land, with 6 sections which will receive randomly applied fertilizer treatments. So how do we randomize the design? Well, the random allocations of treatment to our experimental unit is restricted in such a way that each treatment must occur an equal number of times within each block. So to randomize our design, we would create a random permutation of the order in which treatments are placed in each block. And this is going to provide random allocations of treatments to units. So in this current example, there are 720 possible permutations, and we select one permutation for each block. But it must be noted, you must conduct a separate permutation for each block. Now, we would assign our treatment labels, say A, B, C, D, E, F, and perhaps these are represented by the numbers 1, 2, 3, 4, 5, 6. And then we randomly permute these with the use of a computer or a permutation table. Now, suppose the first block has the following permutation, 1, 6, 4, 5, 2, 3. So this corresponds to treatments A, F, D, E, B, C. And so treatment A goes to unit 1, F goes to unit 2, D goes to unit 3, E goes to unit 4, B goes to unit 5, and C goes to unit 6. I've laid out what we're talking about. Now in block 1, remember we had the permutation 1, 6, 4, 5, 2, 3, and block 1 is field 1. And treatment A, treatment F, treatment D, treatment E, treatment B, and treatment C. And then I've laid out the remaining blocks and their respective permutations. Now we're going to define the response of the unit with the ith treatment in the jth block as, well, we've got Yij equals mu plus tau I plus beta j plus epsilon ij. Here mu is the grand mean, tau I is the treatment mean, beta j is the average deviation of units in block J from the grand mean, and epsilon ij is our experimental error. We'll assume that treatment and block effects are additive. This means that there will be no interaction between treatments and blocks. Also, our epsilon ij's, our errors, are distributed normally with a mean 0 and a constant variance, and these are independent. So, y bar I dot, that's going to be our treatment mean. Y bar 1 dot, then, is mean for treatment 1. Y bar dot j, that's our block means, and so y bar dot 1 is the mean for block 1. And then y bar dot dot is the grand mean. That's the mean of our overall data. We also need some other definitions. Yj, observation in treatment I for block J. T is our number of treatments. B is our number of blocks. Y bar I dot, our sample mean for treatment I. Y bar dot J, our sample mean for block J. And Y bar dot dot, our overall sample mean. Okay, so what does this mean? Well, Y bar I dot then is simply 1 over the number of blocks times we'll sum across the blocks in this particular treatment. So, in other words, Y bar 1 dot, 1 over the number of blocks times the sum of the Yij's in that particular treatment. Y bar dot J, 1 over the number of treatments times the sum of the Yij's in this particular block. And then Y bar dot dot is 1 over the number of treatments times the number of blocks times the sum of the Yij's. So what does this mean? Well, let's look at Y bar 1 dot. What does this mean? Well, we're in treatment 1, and we're going to sum across all of the blocks, and then we'll divide by the number of blocks. Y bar dot 1, we are in block 1. We're going to sum across all of our treatments, and then divide by the number of treatments. And then y bar dot dot, our grand mean, we're going to add up all of our yij's, all of our values, and then divide by number of treatments times the number of blocks. Well, this leads us to sums of squares total, much like we had in our completely randomized design. Except now we have to sum across treatments and blocks, and we take our yij's and subtract off our overall mean, square it, and add all of these up. Our sum of squares treatment then is the number of blocks times the sum of the y bar I dot minus y bar dot dot squared. Okay, so take the group mean, subtract off the overall mean, square it, add them up, multiply by the number of blocks, plus our number of treatments times our y bar dot j minus y bar dot dot squared. In other words, we're going to take our block means, subtract our overall mean, square it, add them up, and then multiply by the number of treatments. And then we have for our sums of squares error, yij minus y bar I dot minus y bar dot j plus y bar dot dot squared. And these can be then put into an ANOVA table. Notice our source now is treatment, blocks, error, and total. Our sum of squares are sum of squares treatment, sum of squares block, sum of squares error, sum of squares total. Our degrees of freedom now are t minus 1, number of treatments minus 1 for our treatment, b minus 1, number of blocks minus 1 for our blocks. However, our error now is b minus 1 times t minus 1. It's degrees of freedom for treatment times degrees of freedom of block. And then if we look at our total degrees of freedom, number of blocks times number of treatments minus 1. Our mean squares. We now have a mean square treatment, which is still our sum of squares treatment divided by degrees of freedom for treatment. Our mean square block is our sum of squares block divided by degrees of freedom of block. And then our mean square error is sum of squares error divided by degrees of freedom for error. Our F value then is mean square treatment divided by mean square error. But notice, I do not have an F value for blocks. This is because we're blocking because we know there are differences. So there's no sense in testing. So next time we'll use a randomized block design in R. See you then.